So in the last couple of sessions, we've migrated a little beyond the rudiments in simple harmonic motion. Now, my class would focus around some of the important things that you're going to encounter in SHM time and again. Now, to begin with, I'm going to get you triggered into two-block oscillations and variations around two-block oscillations. Until my last class, typically I discuss something like this: a spring with a mass at one end, and to extend the spring a little bit, release, it's going to execute simple harmonic motion with omega equal to root k by m, and so on and so forth. Now, the simplest version of a two-block oscillator. The simplest version of a two-block oscillator. Mass m1 connected to mass m2 by means of a spring of force constant k. And the whole system resting on a smooth surface, horizontal surface. M1 and M2 together would have a center of mass. M1 and M2 would together have a center of mass. What I'm going to do is, when M1 and M2 are still at rest, very slowly, very slowly, so that I don't add anything to the kinetic energy of the system, very slowly, I will deform the spring. Very slowly, I'll deform the spring. Either I could bring the masses closer together, or I'm going to pull the masses apart from, this is the natural length of the spring, I'm either going to shove them in closer or pull them apart, either way. And when I release, even at that point of time, the velocity of the two masses is zero, they're at rest. Only after I release the two masses, can I imagine velocity build up in the two masses, because if the spring is compressed, it would want to open up and it would want to throw velocity to the two masses, or if it's elongated, it would want to close in and build velocity in the two masses, right? So the motion subsequent to the release is what I'm going to investigate for this simple two blocks system. Now, one of the things is that, say, if I have pulled the two masses apart, by a certain amount, and the masses are not developing any velocity, while I'm pulling them apart, the masses are not developing any velocity, the spring is, let's say, getting elongated, the center of mass will also not develop any velocity. The center of mass was initially at rest and it continues to be at rest while I'm pulling the masses apart or pushing them in, right? Which means, if the center of mass was at rest initially, it continues to remain at rest subsequently, because even after I release, the two masses develop velocity, but there are no external forces acting on the system, and in the event of an absence of an external force, the velocity of the center of mass will remain constant, because the acceleration of the center of mass is going to be 0. There are no external forces acting on the system comprising M1, M2 and the spring. The forces that act on M1 and M2 are courtesy the spring, and those are internal forces. They will not appear as ones that are going to accelerate the center of mass, right? So, in the entire scheme of things, the center of mass stays put. The x coordinate of the center of mass does not change, right? Even though the masses M1 and M2 down the line would bulge in or bulge out compared to the spring, but the center of mass will stay at the same position all the time. Yes or no? You know what I'm saying? Say, so this you can treat like a wall. This you can treat like a wall. And this whole thing could be looked upon as two springs. This is one spring whose one end is fixed to this point, and this is another spring whose this end is fixed to this point. So this point will not change. You can think of, even though this is one spring, you can imagine it to be two springs. You can imagine it to be two springs. This end fixed to a wall, which is like designating the position of the center of mass. This end connected to the mass M1. For this mass, this end fixed, and this connected to the mass M2, which can execute some kind of a motion, right? So, even as far as M1 and M2 are concerned, you can look at their motions separately. It's as if M1 is like this, and M2 is like this. This being this length of the spring, this being this length of the spring. And these two get concatenated at this point. Right? Now, so one thing, initial velocity of center of mass is 0. F external is 0, which means acceleration of the center of mass is 0, which means the velocity of the center of mass remains 0 all the time. That means the position of the center of mass does not change. The position of the center of mass does not change. Now, see, while M1 and M2 are executing some motion, this is an instant where this is the natural length of the spring. So no force acts on M1 at this juncture, and at the same juncture, no force acts on M2. So this is like an equilibrium position for M1, this is like an equilibrium position for M2, because the spring is in its natural state and does not exert any force on M1 or M2. Now, imagine a situation where M1 is at a distance x1 from its equilibrium position and M2 is at a distance x2 from its equilibrium position. In a state of this kind, call it AA prime, call it the state AA prime, the spring would have elongated by an amount x1 plus x2, the spring would have elongated by an amount x1 plus x2. So then, let me see what happens to M1. This is M1. While in state A, the spring will exert a force Fs direction because the spring is elongated. So the spring will exert on M1 a force in this direction, and it's going to be K times x1 plus x2. x1 plus x2 being the elongation. The spring exerts a force on M1 in this direction, yes or no? Right? And needless to say that if I have pulled the mass by an amount x1 to the left, the force acting on the mass is K into x1 plus x2 to the right. And it's towards the equilibrium position, a position of no net force. Yes or no? So one thing for sure, it's a restoring force. One thing for sure, it's a restoring force and takes place at an instant of time when the displacement of mass m1 with respect to the equilibrium position is x1. Right? So far so good. Now, very clearly, when x1 and x2 have drifted to the left and the right, as shown, the center of mass is where it was. Right? Let me say that everything to the left is positive and everything to the right is negative. So then, in our attempt to compute the position of the center of mass, summation mixi by summation mi, this one would have caused an increase of, between this state and this state, there would have been an increase of m1 x1. The contribution made, the incremental contribution made by this one, when this moves to the left, is m1 x1 to the numerator of mixi. Or just in case you don't feel comfortable with it, let me think of it as follows. Say, this was the L direction, Then the L coordinate of the center of mass, is going to be, say, m1 L1 plus m2 L2 by m1 plus m2. In this state, this was L1 and this was L2. This would be the L coordinate of the center of mass. Yes or no? Now, when the two masses m1 and m2 are in their final states, A and A prime, then this L1 becomes L1 plus x1 and this L2 becomes L2 minus x2. So then the center of mass becomes m1 L1 plus x1 minus plus m2 into L2 minus x2 by m1 plus m2, and that will also give me L coordinate of the center of mass. The same L is going to be obtained, right? Now, evidently, for the numerator of this to be the same as the numerator of this, m1 x1 minus m2 x2 must be 0. m1 x1 minus m2 x2 must be 0, so that this eventually is rendered m1 L1 plus m2 L2 to preserve the position of the center of mass. m1 L1 must be, m1 x1 must be equal to m2 x2. Yes or no? You know what I'm saying? So then, very clearly in this state, m1 x1 is m2 x2. m1 x1 is m2 x2. I can replace this x2 by m1 x1 by m2. So then the restoring force becomes x1 plus m1 x1 by m2, replacing this x2 by m1 x1 by m2 x2, right? Which then is like a k times m1 plus m2 by m2 into x1. That's the magnitude of the restoring force, which is proportional to x1, the displacement from the equilibrium position, So this, the motion of m1 obviously is simple harmonic, where the k of the system is k into m1 plus m2 by m2, right? So the omega square for m1, would be this divided by m1. The omega square for m1 would be this divided by, this is the force constant. This divided by m1 will give me the omega square for m1, yes or no? Right? So for m1, the omega square becomes the force constant for m1 divided by m1, right? Where in common parlance, m1 m2 by m1 plus m2 is commonly referred to as mu, the reduced mass of the combination, is commonly referred to as the reduced mass of the pair. So then I could write this as omega could be written as root k by mu. K is the force constant of the spring and mu is the reduced mass of the system. Then mass m1 would execute simple harmonic motion with angular frequency equal to root k by mu. Right? Now, one thing. When you look at m2, similar things would happen. Again, this will become m2 m1 by m1 plus m2. And the k will still be the same as the k earlier. The spring will make its appearance as k right here. And this mu would be like m2 m1 by m1 plus m2, which is the same. So m2 will also execute simple harmonic motion with the same omega. m2 will also execute simple harmonic motion with the same omega. Yes or no? So both m1 and m2 execute simple harmonic motion about their equilibrium positions, which are commensurate with the natural length of the spring. The center of mass stays put, and this becomes the angular frequency of the two oscillators m1 and m2. So as far as m1 is concerned, you can imagine m1 to be executing simple harmonic motion with this end being connected to a wall, which is the center of mass at rest, with an omega equal to root k by mu. Mu is the reduced mass of the system. As far as m2 is concerned, same, as if this end is fixed, connected to a wall, and it will execute simple harmonic motion with omega equal to root k by mu. Yes or no? Right? Now, for the same system, this was the natural state of the spring, also commensurate with the equilibrium positions of the two masses. And I then want to be able to compute the amplitude of the motion. Hey, suppose they have the same omega. The two masses have the same omega, but not necessarily the same amplitude, which is what I'm going to demonstrate to you now. Suppose in the initial stage when I'm trying to trigger the system to an expansion or a compression, I pull masses m1 and m2. Let's say m1 is pulled by an amount a1 to the left and m2 is pulled by an amount a2 to the right. So what's the elongation that I'm producing in the spring? a1 plus a2. Or I could have compressed m1 by an amount a1 and I could have compressed m2 by an amount a2. So then the compression in the spring would have been a1 plus a2. Same thing, it does not matter. Either way, I can initiate simple harmonic motion by either a compression or an elongation. It does not make any difference. So now I would know how much length of the spring I have elongated. Alright. I would know a1 and a2 to begin with. All that I know is I've pulled the masses apart in a manner that the center of mass is at the same position. And in the process, m1 gets automatically pulled by an amount a1 and m2 gets pulled by an amount a2. So now what would be known to me is not a1 and a2 but a1 plus a2, which would be x0, the initial elongation or the initial compression that I have plunged. Initial elongation or the initial compression that I have given to the system x0. A1 and A2 I'm pretending that I know, right? Now, whatever it be, so you also realize that if this was the center of mass, it's as if mass m1 is connected to the wall by means of the spring and it's fixed here, right? So then the amount by which I slowly pull mass m1 to the left will give me the amplitude of motion of m1. So this a1 actually is the amplitude of m1 and that a2 is the amplitude of m2. But again, to preserve the center of mass, I must still have, like I demonstrated a little while ago, m1 a1 equal to m2 a2. To preserve the location of the center of mass, like I had a m1 x1 equal to m2 x2, I must have m1 a1 equal to m2 a2. And from these two equations, I can calculate the values of a1 and a2, the amplitude of motion. Obviously, someone would have to subscribe to x0. x0 would have to be given the amount of compression or elongation that I produce in the spring initially, right? And very slowly. This is on the premise that the whole thing is done very slowly, all right? For academic interest, let me again give you a different view to this. So far so good, right? You understand that the omega, the angular frequency of oscillation of the two masses would be the same. It's going to be root k by mu. However, their amplitudes would be determined by these two conditions, right? Now, just to offer to you a little bit of a different view on the whole thing. Say this is the unstretched length of the spring. This is the unstretched length of the spring. K is the force constant of the spring. Y is the Young's modulus of the material of which it is made of. Y is the Young's modulus of the material of which it is made of. Now say this length is L1 and this length is L2. This length is L1 and this length is L2. Right? So I can think of M2 to be influenced only by a spring of length L2, right? And a shorter length will have a different force constant, right? This L2 is less than L. So the force constant of this portion will be different than K. K is the force constant if the length of the spring was L, right? So M2 could be looked upon as being under the influence of a spring of length L2, whose force constant we can calculate based on the fact that the force constant for the same material is going to be K given a length L, right? Similarly, M1 is under the influence of a spring of force constant, let's say K1, which is this length of the spring L1, whose force constant obviously will be different than the force constant of a length L, right? So if I can compute the K1 for this, and I can compute the force K2 for this, then I know this is mass M1. This was the center of mass, which is like a wall. This is K1. Then we've seen in my previous class that the omega for this is going to be root K1 by M1. I've demonstrated this in my last class, right? And for M2, there is this length L2 with force constant K2, and the omega for this length is going to be root K2 by M2. Yes or no? So then, if I can calculate K1 and K2, then I would know omega 1 and omega 2 of the two masses in a scenario of this kind. Right? Now, K, the force constant, is AY by L. A is the area of cross section. A is the area of, I gave you this in an earlier session. The force constant of a spring, linear spring, is going to be A, which is the area of cross section of the spring. Y which is the modulus of elasticity for the spring, L the length of the spring. Which means for a spring having the same area of cross section and the same y, K into L will be a constant. K into L will be a constant. Yes or no? Because K into L will be area of cross section into y. So for this part of the spring, same A. For this part of the spring, same A. Same material, so y of this is the same as y of this. Yes or no? So can I not say that K into L, which is for the bigger spring, must be equal to K1 L1 for the spring, must be equal to in turn K2 L2 for the spring, right? Right? So K1 then from these considerations is going to be KL by L1 and K2 is going to be KL by L2. Yes or no? K1 and K2 would be KL by L1 and K2 would be KL by L2, right? Now, in order to explicitly determine K1 and K2, I just need to know the values of L1 and L2, which is how, this was the unstretched length of the spring, and how far was the center of mass from M1 and how far was the center of mass from M2. Those would give me L1 and L2. Clear? Hey, if I have two masses, say M1 and M2, right? Say this was L equal to 0. This was L equal to 0. This was L equal to L, the length of the spring. This was L equal to L, the length of the spring, initial length of the spring, right? So now if I have to compute the L of the center of mass, L of the center of mass would be essentially L1. L of the center of mass would essentially be L1, which is going to be what? M1 into 0 plus M2 into L divided by M1 plus M2, yes or no? Right? So M1 into 0 plus, so that's going to be M2 into L by M1 plus M2. And this L of the center of mass is going to be L1, is going to be L1. So L1 is known. Similarly, so if L1 is known, L2 obviously would be L minus L1, L minus L1, and L2 will turn out to be M1L by M1 plus M2. That's L2. Right? Are you fine with all of this? Right? Now, what is K1 therefore? K1, as you can see from there, is KL by L1, KL by L1, right? And L by L1 is M plus M2 by M2. L by L1 is M1 plus M2 by M2. That's K1. And this K1, now you plug into this, the K1 that we have computed when you plug into this will give you root K into M1 plus M2 divided by M1 M2. But M1 M2 by M1 plus M2 is mu, the reduced mass of the system. So it will turn out to be root K by mu. And if omega 1 turns out to be K into M1 plus M2 by M1 plus M1 into M2, then replace M1 by M2 and you replace M2 by M1, you will get omega 2. So which is also going to be the same. So the two masses execute simple harmonic motion as if they are pinned at the center of mass, and they execute simple harmonic motion of the same angular frequency and therefore of the same time period given by root K by mu, the reduced mass. Right? So when you look at M1 and M2 from the center of mass, they would execute simple harmonic motion with the same omega, and I have already told you how to compute the amplitude of motion of the two masses. Clear? Now let me vary this. This was a baseline understanding of the two block oscillator, right? where all that I did was I made sure that everything happened in a quasi-static manner. I did not cause the center of mass to get dislodged while I was initiating the motion. I made sure that everything took place so slowly. All the initial expansion or compression took place in a manner that the center of mass did not develop any velocity and therefore it stayed in position all the time. Right? Let me vary the situation a little bit. Let's say there is a 3 kg block, call it A, connected to a block B, which is a 2 kg block, and this is the natural length of the spring, L, natural length of the spring, call it L naught. This is the center of mass initially. This is the center of mass initially. Now, say I give the 2 kg block an impulse to the right. I give the 2 kg block an impulse to the right, and the block develops a velocity of 2 meters per second. Block then develops a velocity of 2 meters per second, such is the impulse. Right? All of this is at time t equal to 0, when the spring is still in its natural state. An initial velocity of 2 meters per second. Now, look at things not from a ground observer's perspective. Look at things, analyze the system in the perspective of a center of mass observer, a center of mass observer. One thing, at time t equal to 0, what I have done is by giving an impulse to B, I have built up velocity in the center of mass. Right? What's the velocity of the center of mass when I do this? 3 into 0, because this will not instantly react. 3 into 0 plus 2 into 2, 4 divided by 5 meters per second, 0.8 meters per second to the right is the velocity of the center of mass. Is the velocity of the center. Second. Right? And this has a velocity v naught prime equal to 0. What I do is, I reduce the system to the one that we've already analyzed. The earlier system had 0 velocity of the center of mass, but this does not have 0 velocity at the center. But now if you are an observer sitting at the center of mass, then the velocity of the center of mass becomes 0. Yes or no? I revise this system. I make myself an observer stationed at the center of mass, in which case the velocity of the center of mass is 0. But then the moment I start looking at things from the center of mass perspective, then I need to justify the same. In the center of mass frame, so to say, the velocity of the center of mass will be 0. In the center of mass frame, the velocity of the center of mass is 0. The velocity of B is now going to be 2 minus 0.8, 1.2 meters per second to the right. Velocity of A is going to be 0 minus 0.8. That means minus 0.8 to the right means 0.8 to the left. The velocity of A is going to be 0.8 meters per second to the left. Yes or no? Right? And now if I'm seeing everything in the center of mass frame perspective, everything in the center of mass frame perspective, then in principle, this is like a fixed wall. B is in its equilibrium position here. B is in its equilibrium position here. Right? B, because no force is acting on B and it has a velocity of 1.2 meters per second. A is in its equilibrium position here. No force acts on it and it has a velocity of 0.8 meters per second to the left. Right? And therefore, you would expect A and B to execute simple harmonic motion as reported only by the center of mass observer. Right? As reported by the center of mass observer, it's going to execute simple harmonic motion. Right? Let's say K of the spring is 120 Newton per meter is the K of the spring. Right? So the omega of oscillation in the center of mass frame, the omega of oscillation, because omega is only in as far as the center of mass frame is concerned. It's going to execute simple harmonic motion in the center of mass frame, only in the center of mass frame, with omega equal to root K divided by mu, the reduced mass of the system. With these many radians per second, it's going to execute simple harmonic motion in the center of mass frame perspective. Clear? Which is going to be, say, 120 divided by 10 radians per second. 10 radians per second is the omega in the center of mass frame. Right? Now, what's the amplitude in the center of mass frame? Very good, very good. So then the amplitude in the center of mass frame could also be computed because I have knowledge of the total energy of the system in the center of mass frame. There is no reason that will prevent me to calculate the amplitudes of the oscillations of A and B in the center of mass frame. Right? So if A1 is the amplitude of A, realize that 0.8 meters per second is the velocity at the mean position. So 0.8 V in the mean position must be omega, which is 10 into amplitude A1. Yes or no? Right? So A1 is known, 0.08 meters. Amplitude of B, the velocity at the mean position is 1.2 meters per second with respect to the center of mass. Must be omega, which is 10 into A2. So A2 then is going to be 0.12 meters. Right? So the center of mass frame observer would very keenly report to you that both A and B are executing simple harmonic motion with these amplitudes and with angular frequency equal to 10 radians per second. That's what the center of mass frame observer would tell you. The ground frame. What the hell is it? What's the problem? No, I must warn you that you've got it once from me and you might want to maintain a body language which is acceptable to me. If you know it all, then go out here, come here and teach. I have no problems letting you teach. if you know this. But if you don't know this, then maintain an acceptable body language here, right? You know what I'm saying? Yes. Feel sorry about it. Now, very clearly, say this was x equal to 0. This was x equal to 0. So, from the center of mass frame, this will execute simple harmonic motion with amplitude A2. So, at t equal to 0, x was 0. In the center of mass frame, at t equal to 0, x was 0. So, you can very clearly say that x of b in the center of mass frame, the displacement of b t seconds later is going to be a2 sine omega t. See, at t equal to 0, x is 0 and it's moving to the right. So, in the center of mass frame, the displacement of b is going to be given by a2 sine omega t. Yes or no? Because in general a2 sine omega t plus phi, but phi is 0 because at t equal to 0, x is 0 and it's moving to the right. So, the displacement in the center of mass frame, the displacement of b in the center of mass frame is going to be given by a2 sine omega t. In the center of mass frame, it's going to move away by a2 units and then going to come closer by a2 units. That's why with this as the equilibrium position, right? That's the center of mass frame. Now the ground frame. The displacement of b in the ground frame is not going to be the same. Because in addition to this, the ground frame will also see a bodily movement of the center of mass. T seconds later, in the center of mass, this would have happened in the center of mass frame. This would have been the displacement of the T seconds later, yes or no? But in the ground frame, that means with respect to a ground observer, the displacement would just not be this. It would also be by what amount the center of mass has drifted to the right. In T seconds, realize that the velocity of the center of mass is 0.8 meters per second. So the displacement of the center of mass with respect to the ground in T seconds is going to be 0.8 T. The velocity of the center of mass is not going to change. Why? Because there are no external forces acting on the system. So the center of mass would continue to move to the right with a velocity of 0.8 meters per second. So the displacement of B in the ground frame, is going to be 0.8 T, which is the displacement of the center of mass, right? Plus the displacement with respect to the center of mass. The displacement with respect to the center of mass is going to be a2 sine omega t. So this is the displacement characteristics in the ground frame. This is the displacement characteristics in the center of mass frame. Do you understand all of this? Right? Now, one of the things that I want to mention to you is that let's say there is a system comprising two blocks and they're connected by an ideal spring, right? And at some instant, let's say the spring was unstretched, the spring was in its natural state, and at such an instant, the velocity of this mass was m1 and the velocity of this mass was m2. For definiteness, only for definiteness, let's assume that V1 greater than V2. Only for definiteness, let's assume that V1 is greater than V2. Velocity of one end is larger than the velocity of the other end. And the spring is in its natural state. Clear? Now, what's going to happen to the spring? What's going to happen to the spring? Since this end has a velocity larger than this end, the spring will get compressed. The spring will get compressed. While the spring gets compressed, it's going to experience retardation from the mass m1 will experience retardation from the spring, and the mass m2 would experience acceleration, right? Because force, the spring force acts in this manner. So m1 retards, whereas m2 accelerates. Which means typically starting from t equal to 0, the velocity of m1 will decrease. Velocity of m1 will decrease, say v1 decreases, right? Whereas velocity of m2, which is v2, increases. v2 increases starting from t equal to 0. This is what happens at some instant of time t equal to t naught. They acquire a common velocity vc. Right? But until this instant of time t naught, this has a larger velocity than this, and it will keep getting compressed. But after a while, the velocity of this becomes equal to the velocity of this. Right? The spring will not compress any further. When the velocity of this becomes equal to the velocity of this, the spring will not get compressed any further. In fact, beyond this point, beyond t equal to t naught, the velocity of m2 will increase, the velocity of m1 will decrease. So that means t equal to t naught must represent the state of maximum compression of the spring. T equal to t naught must represent the state of maximum compression of the spring. Are you all okay with this? Right? In general, make a note of things. Whatever I have said of compression is also true for elongation. Write down. In a typical two-body system, the state of maximum extension or maximum compression of the spring, the state of maximum extension or maximum compression of the spring takes place at an instant when the velocities of the two masses is the same. That is when their relative velocity becomes zero. So be it maximum extension or maximum compression, at an instant when a maximum or minimum takes place, that means maximum extension would be maximum length of the spring. Minimum extension would be minimum length of the spring. So the maximum length of the spring or minimum length of the spring would be in a state where the velocities of the two masses connected at the ends is the same. This is very important, and this fact will be used time and again, used very often. That is when their relative velocity becomes zero. say K equal to 1120 Newton per meter. The spring is in its natural state to begin with. The spring is in its natural state to begin with. And this has a velocity V naught equal to say 10 meters per second. And this has a velocity at this juncture V naught prime as 3 meters per second. Right? And I then want to compute the maximum extension in the spring. I then want to compute the maximum extension. The spring will extend right now. Why? Because see, this point has a velocity larger than this point. The spring will elongate, right? So it will keep elongated. It will keep elongating till such time that their relative velocity becomes 0. The velocities of the two masses becomes the same. Okay. So, which means what? Let's say at an instant, first of all, what's the velocity of the center of mass? Velocity of the center of mass is going to be 20 plus 15 divided by 7, which is 5 meters per second is the velocity of the center of mass to the right. And it will remain 5 meters per second. Even though the velocities of the two constituent masses will wax and wane, the velocity of the center of mass will always be 5 meters per second. Why? Because there is no acceleration of the center of mass. Why is there no acceleration of the center of mass? Because there is no external force acting on the center of mass. Clear? For sure, in the center of mass frame, the two masses will execute simple harmonic motion with omega equal to root A, which is 1120 divided by the reduced mass, which is m1 m2 by m1 plus m2. Yes or no? 10 by 7. Right? So that makes it 7 into 16, so 7 squared into 4 squared, so 28 radians per second is the omega. In the center of mass frame, m1 and m2 are seen to execute simple harmonic motion with angular frequency equal to 28 radians per second. Yes or no? Right? Now, again in the center of mass frame, I will first of all solve this problem without using the center of mass, from first principles only. From first principles, let me find the maximum elongation in the spring, and then we will see what happens later. What we figured out is that in a state of maximum extension or maximum compression, the velocities of the two masses must be the same. If the velocities of the two masses is the same at a certain instant, then that must be the same as the velocity of the center of mass. Yes or no? No. Right? If at a certain instant of time, the velocity of this becomes equal to the velocity of this, then each must be equal to the velocity of the center of mass. Yes or no? Right. So that means the final common velocity when the extension is a maximum must be 5 meters per second for both the masses. Yes or no? Right. So in a state of maximum elongation, velocity of A is equal to velocity of B. Each must be equal to the velocity of the center of mass, must be equal to 5 meters per second. Right? Now, let's say x is the elongation that occurs at this point of time, right? Till this point of time, x is the elongation. So, there are no dissipative forces acting on the system. There are no dissipative forces acting on the system. So, I can conserve the total amount of energy which which shuffles between the kinetic energy of the two masses and the elastic potential energy of the spring. What did we start with? We started with kinetic energy of A and kinetic energy of B, which is like half of 5 into 3 squared plus half of 2 into 10 squared, right? This is the total amount of energy that we started with. Kinetic energy of the two masses, the spring was relaxed. No elastic potential energy associated with the spring. And in this state, half ma va squared plus half ma vb squared. So half of ma plus mb, which is half of 7 into 5 squared. Half of, this is the kinetic energy that remains, plus half of a x squared, where x is the maximum compression, No? Yes or no? So this would enable computation of x. The maximum elongation that takes place in the spring. Yes or no? Let me handle it a little differently now. So far so good, right? All of you understand the criteria involved here. No confusion, right? Now let me handle it a little differently in the center of mass perspective. So if I'm looking at both the masses A and B in the center of mass frame, then if I reduce this to 0, then the velocity of B must be 10 minus 5 meters per second to the right. In the center of mass frame, the velocity of B must be 10 minus VCN, which is 5 meters per second to the right? This is center of mass frame. Now, velocity of A must be 3 minus 5 minus 2 meters per second to the right. That means 2 meters per second to the left. It's as if the velocity of the center of mass is 0, right? This is the adjustment made. So in the center of mass frame, this would move to the right and would go all the way to its amplitude position. This would move to the left and would go all the way to its own amplitude position, right? So this would move, let's say, A2 units to the right at best. This would move A1 units to the left. So then A1 plus A2 would be the maximum elongation. A1 plus A2 would be the maximum elongation, all right? So then how do you compute A1 and A2? The velocity, these are the mean positions of the two masses, right? So the velocity of the mean position 2 meters per second must be omega, which is 28, into amplitude A1. Say A1 would be 2 by 28. A1 would be 2 by 28. And this 5 meters per second must be omega, which is 28, into A2. So A2 would be 5 by 28, right? So the maximum elongation is going to be A1 plus A2. Yes or no? Seven by 28, 1 by 4 of a meter. 25 centimeters is the maximum elongation. So the problem gets significantly reduced in bulk when you look at it from the center of mass perspective, right? Not a problem, right? This is another way of looking at it. The same thing. This is another way of looking at it. Say this was A, mass m1, this was B, mass m2. The spring was relaxed and the velocity of the center of mass could be computed by m1 v1 plus m2 v2 by m1 plus m2. The velocity of the center of mass could have been obtained, right? Now realize that the total amount of energy that the system has in the state is purely kinetic. To begin with, it has purely kinetic. So that's going to be total energy E total. E total is half m1 v1 square plus half m2 v2 square. Yes or no? That's the total energy in the system. Of this total energy, there is some amount of energy which is kinetic energy of translation, which is kinetic energy of translation. Of this total energy, part of it resides as kinetic energy of translation. What is that? E translation is going to be half of m1 plus m2 into vcm squared. This is the kinetic energy which is embodied in translation. That means, after all, in this system, two things are simultaneously occurring: translation and oscillation. Translation and oscillation, that's how it's proceeding, right? This is the total amount of energy of which this is translational. This minus this must be oscillation energy. This minus this must be oscillation energy. The total amount of energy in oscillation is going to be E total minus E translational. And this oscillation energy is shuffles between kinetic energy of the two masses and the elastic potential energy of the spring. So when this oscillation energy gets completely converted, into elastic potential energy of the spring, then that must give me the maximum elongation. Yes, sir. So when this gets converted into elastic potential energy completely, half kx max squared, this will give me the maximum elongation. It's going to give me the maximum elongation. So this is another way of looking at it. Right? So x max could also have been obtained with this in mind. Compute the total energy, the translational energy, and therefore the oscillational energy. Just the oscillational energy. And when this oscillational energy gets completely translated into elastic potential energy, it's going to give me the maximum elongation or even the maximum compression, as the case may be. Maximum elongation or the maximum compression as is relevant. Right? I mean, if V1 greater than V2, it will be a case of maximum compression. If V2 greater than V1, it's going to be a case of maximum elongation. Yes or no? Right? The important thing you have to know all the time is that in a state of maximum elongation or maximum compression, the relative velocities of the constituent masses must be zero. That's the important thing that you have to bear in mind. Let me change the situation a little bit now. All along, I have been dealing with the velocity of the center of mass constant, either zero or non-zero. But now again, let me look at a two-block oscillator on which a constant force F acts on one of the masses, right? And then I would want to compute the maximum or maximum elongation, maximum compression, etc. This is a natural length of the spring in its relaxed state, and the two masses are initially at rest. The two masses are initially at rest. And a force, constant force F acts on one of the masses, say M2. A constant force F acts on one of the masses, say M2. And let's say the initial length of the spring is L0, which is the natural length of the spring. I want to compute the maximum length the spring attains. I want to compute the minimum length the spring attains. Right? One thing, this is not a case where the acceleration of the center of mass is zero. In this case, there is a net external force acting on the system comprising M1, M2 and the spring, which is F. So the center of mass evidently has an acceleration ACM to the right. The center of mass has an acceleration ACM to the right. But I will look at things in the center of mass frame later on. Let me look at it more fundamentally in the ground frame first. Let me look at it more fundamentally in the ground frame. So this was t equal to 0, the spring was relaxed. T seconds later, let's say the spring underwent an elongation x. The spring got elongated by an amount x in t seconds, right? Elongation in t seconds. So there would be spring force kx developed at that point of time. There would be spring force developed at that point of time. And at that point, when the spring has got elongated by an amount x, spring is elongated, so it's going to exert a force kx on M1 like this, right? And on M2, it's going to exert a force kx leftwards. Yes or no? Right? Along with it, there is a prevalent constant force F acting to the right. By this time, both M1 and M2 would have developed velocities, V1 and V2, say. Right? Now, let me write Newton's second law for M1 and M2. For M1, what's the only force acting on M1? Kx? Kx must be M1 dV1 dt. Newton's second law, right? For M2, right? F minus Kx equal to M2 dV2 dt, right? Now, what I do is I allow this M1 to come here. I allow this M2 to go there. Let me write an expression for ddt of V2 minus V1. This minus this, this minus this. If I subtract now, 2 minus 1 equation 2 minus equation 1, then I have ddt of V2 minus V1. ddt of V2 minus V1, right? If I subtract, this is what I end. Reason I subtract is because, for maximum and minimum elongation, I need relative velocity. So V2 minus V1 will allow relative velocity to seep in the picture, right? So ddt, this would give me F by M2 minus, if I combine these two, minus Kx into 1 by M1 plus 1 by M2, right? So this is like a Kx by mu. Do you realize that this is like a Kx by mu? Mu is the reduced mass m1 m2 by m1 plus m2. Right? Now ddt of v2 minus v1. v2 minus v1 is the relative velocity. Yes or no? Is v, which is relative velocity. Yes or no? Is the relative velocity v. So this is like dv dt. Right? Can I write this as v dv dx? dv dx into dx dt. The dx dt is also relative velocity, right? So v dv dx, I could write this as v dv dx. Make sense? Okay. So then ddt, where x is the elongation, instantaneous elongation. So then this I write as v, where v is the relative velocity when the elongation is x. V is the relative velocity when the elongation is x. So v dv dx. So we have a firm ground set to calculate the relative velocity as a function of elongation x by integrating this. You know what I'm saying? v dv is f by m2 minus kx by mu into dx. Right? Obviously, you want to now integrate both sides. In the initial state when x was 0, no elongation, we started with no elongation. So initially x was 0 when the spring was in its natural state, relaxed state. The relative velocity was 0 because both masses had 0 velocity to when we started, right? And when x is x, when v is, say v, when x is x, let's say v is v. So this will give me v relative velocity as a function of elongation x, as a function of elongation x. So I get v squared by 2 when I supply the limits is f by m2 into x minus kx squared by 2 mu. And when I plug in this equal to 0, that means relative velocity is 0, I'll get two values of x, right? For x max or x min, right? I put relative velocity as 0, relative velocity is 0. This will give me one of the values obtained would be x equal to 0, right? That's a maximum compression. That means there is never a compression in this. That means the minimum length is L naught in this. The minimum length is L naught. X, one of the values that I get is x equal to 0, right? The other value of x that I get will correspond to 2f mu by kmt, m2. See, the other value of x is going to be 2f mu by km2, by km2. So this would be the maximum elongation. That means the minimum length of the spring is the original length L naught plus 0. The maximum length of the spring is going to be L naught plus 2f mu by km2. Are you all right with this? Did you understand this? I'll wait for you to copy. Huh? No. It will never fall below its, in this case, as you can very readily judge, it will never fall below its natural length. It will never fall below its natural length. Right? Why not look at the same situation in the center of mass frame perspective? Right? Are you assimilating everything? Right? So now let me examine this in the center of mass frame, and not with the help of Uncle Newton, but with the help of work energy perspective, right? In a work energy domain, let me examine this problem in the center of mass, frame. Acceleration of the center of mass is going to be F by m1 plus m2. Now, in the center of mass frame, that means that this is my observer. So this is an accelerated observer, a non-inertial observer, isn't it? The center of mass observer is a non-inertial observer, isn't it? So in the center of mass frame, I'm going to deploy a pseudo force minus ma naught. A pseudo force will be required at the moment I confine myself to an accelerated observer. Then I would have to make an adjustment on the system to the tune of minus ma naught wherever relevant, right? So then there is a force m2 into ACM acting on it like this, pseudo force m2 into ACM acting on it like this, m2 into ACM acting on it like this, right? And there is going to be a force m1 into ACM acting on it this way. This is the force scenario. And this was t equal to 0. This was t equal to 0. Let's say at an instant of time t, as seen by the center of mass, m1 drifts leftwards by an amount x1. Say m1 drifts leftwards by an amount x1 and m2 drifts rightwards by an amount x2. So in the center of mass frame, m1 deviates by an amount x1 leftwards and m2 deviates to the right by an amount right. So between t equal to 0 and t equal to 2t, this is t equal to t, this is t equal to 0. I'm going to apply work energy theorem. In the center of mass frame, I will apply work energy theorem. So if I apply work energy theorem in the center of mass frame, the displacements relevant would be displacements as seen by the center of mass observer. Now, one thing, the elongation in the spring up to this instant of time is x1 plus x2. Yes or no? Because this is moved to the right by an amount x2, this is moved to the left by an amount x1 as seen in the center of mass frame. So the elongation in the spring is x1 plus x2. Yes or no? Right? Now, if this x1 plus x2 is a maximum or a minimum, then the velocity of m1 at this instant will be the same as the velocity of m2 will be the same as the velocity of the center of mass. That means the velocity of the two masses in the center of mass frame at this juncture would be 0. Yes or no? If this is maximum or minimum, if this is maximum or minimum, then the velocity of the two masses in the center of mass frame must be 0. Both must have a velocity equal to the velocity of the center of mass at this time. Yes or no? So in the center of mass frame, velocity of m1 equals velocity of m2 equals 0. These are velocities in the center of mass frame. In the center of mass frame, the velocities must be 0. That means in the ground frame, both m1 and m2 must have the same velocity as that of the center of mass, right? Alright. Initially also, the velocity of m1 and m2 in the center of mass frame was 0, isn't it? Because we had the system start from rest. Center of mass at 0 velocity, this had 0, so velocity in the center of mass frame initially also was 0 for m1 and m2. Okay. So now, the closing remark here is about applying work energy theorem between t equal to 0 and t equal to t, where the elongation x1 plus x2 is the maximum or work done by various forces. Work done by F is going to be F into x2. Work done by F is going to be F into x2, right? Work done by M2 ACM. See, this is leftwards, but x2 is rightwards. So work done by this is going to be minus M2 ACM into x2. Work done by the pseudo force, because x2 is to the right, the pseudo force is to the left. Work done by M1 ACM. Now this displacement is x1 to the left. So work done by M1 ACM is this into x1. There is also spring force. Work done by the spring force is negative of the change in elastic potential energy. Initially elastic potential energy is 0. Final elastic potential energy is half k x1 plus x2 whole square. Yes or no? So negative of the change in elastic potential energy is minus half k x1 plus x2 whole square, minus half k x1 plus x2 whole square. This must be change in kinetic energy in the center of mass frame. Final kinetic energy in the center of mass frame minus initial kinetic energy in the center of mass frame. Hey, what's the final kinetic energy in the center of mass frame? 0. What's the initial kinetic energy in the center of mass frame? 0. The velocity of m1 and m2 finally, as seen by the center of mass frame, is 0. So kinetic energy of m1 and m2 in the center of mass frame finally is 0, and initially obviously it was 0. So change in kinetic energy is 0 in the center of mass frame. So far so good, right? And then, after all, what's my objective? My objective is to calculate x1 plus x2, x1 plus. So it seems like a very ugly looking heterogeneous expression, x2, x1 separate and then x1 plus x2. My focus is on x1 plus x2. My focus is on x1 plus x2. And I want to have two values of x1 plus x2 available. One will give me minimum, the other one will give me maximum. Clear? Well, no big deal, because realize that this ACM I can write by as F by M1 plus M2. I have replaced the ACM, the acceleration of the center of mass, by F by M1 plus M2. If I took Fx2 common from this, then I'll have Fx2 into M1 by M1 plus M2 plus fx1 see this fx2, so m1 by m1 plus m2, then m1 x1 f by m1 plus m2. Yeah. Evidently this is fm1 by m1 2 into x1 plus x2 minus half k x1 plus x2 whole square. Good for us. Okay, the same thing that we got last time. So if I take x1 plus x2 common from this, I'll get two values of x1 plus x2. One is x1 plus x2 equal to 0. The other one is x1 plus x2 equal to 2 this divided by k. These are the two values of x1 plus x2. One giving me a maximum and the other one giving me a minimum. Make sense? Sometimes a typical two-body oscillation is also a little camouflaged. In this case, it's very distinct. Two blocks, M1 and M2 connected by a spring and so on and so forth. There are times when they would camouflage it a little bit. Can I write this off? Have you understood everything that I have communicated so far? Right? There is a trolley of mass M. Right? There is a spring and this structure, this strut fixed rigidly to the trolley is supposed to become integral with the trolley. All surfaces involved are friction ratio. The spring initially in its nature. So what will happen? Nothing. Why would anything happen unnecessarily, right? So if you want something to happen, you will have to do something. What you do is, you compress the spring. You compress the spring, alright? Let's say you compress the spring, or you could even elongate the spring. It does not make any difference, right? So you compress the spring, say by an amount x naught. Right? You compress the spring by an amount x naught. And you do that very slowly so as to not disturb the center of mass of small m and capital M. You do it in a manner without disturbing the center of mass of small and capital M together. Right? You know what I'm saying? But then, to compress the spring by an amount x naught, it's as if you will have to move the mass m1, small m by an amount 1. You will have to move the mass small m by an amount x1 as seen by a ground observer. The mass m moves by an amount x1 and the trolley moves to the right by an amount x2. That means this point moves to the right by an amount x0 and this point moves to the left by an amount x1. So the compression of the spring is going to be x1 plus x2. Compression of the spring is going to be x1 plus x2. You know what I'm saying? So x1 plus x2 would actually have to add up to x0. If this capital M was rigidly fixed to the ground, then x1 would have been equal to x0. But since this is capable of moving, to compress the spring by an amount x0, mass M moves to the left by an amount x1, mass capital M moves to the right by an amount, where x1 plus x2 must be equal to in any case. The spring gets compressed by an amount x1 plus x2. The mass has drifted to the left by an amount x1, the mass small m has drifted to the left by an amount x1, and the spring force is going to be k times x1 plus x2, right? So if you now look at the force on the mass small m, this was the state where there was no net force acting on the mass m. Why? Because the spring was relaxed, right? So this could be looked upon as an equilibrium state. When the mass is displaced with respect to the equilibrium state by an amount x1, a spring force, the spring force of magnitude k times x1 plus x2 is going to act on the mass m, and it's a restoring force because it's directed towards the equilibrium position. Hey, again, to preserve the x coordinate of the center of mass, like I discussed at length, m into x1 must be capital M into x2, yes or no? To preserve the x coordinate of the center of mass, small m into x1 must be capital M into x2, right? So this x2 I can replace by mx1 by capital M. That's a restoring force. That's a restoring force acting on small m. So k times x1 plus x2, which is small m x1 by capital M, right? Which is k times m plus small m by capital M to x1. Restoring force proportional to the displacement from the mean position. The motion of small m has to be simple harmonic with the force constant being this, right? So the omega square of the oscillation, is going to be k into capital M plus small m by capital M divided by small m, right? So, but capital M into small m by capital M plus small m is mu, the reduced mass. Capital M into small m by capital M plus small m is mu. So the omega is going to be root k by mu. Mu is the reduced mass, capital M into small m. Essentially the same as the earlier one, right? Same with capital M. Capital M will also execute simple harmonic motion with this omega, and their amplitudes could be computed as A1 plus A2 must be A0 and M1 A1 must be equal to M2 A2 would give you an opportunity to calculate the amplitudes of motion. Got me? Right? So this is what I said, this is a camouflaged version of a two block oscillator. This is how it is, but then basically the same. Sometimes they might just want to do a little, they might want to make it a little uglier in the sense, you know, this is small m, trolley, we'll put two springs like this. It's just going to double. See, essentially then the two springs are in parallel. Do you realize that? There are two springs in parallel when their ends are in the same kinematic state. The end of the spring and the end of the spring, same state. Their other ends are also in the same state. So this whole thing can be replaced by one single spring of k equal to k plus k, 2k. So this whole thing is like two springs in parallel. The k's would be the sum of the k's. mass m, this is 2k, and then same as before. So in the earlier expression root k by mu, you say root 2k by mu, root 2k by mu, all that you want.